Welcome to the introduction video on R. So in this video, we will learn how to download R software, RStudio in particular, install some key packages, do some basic mathematical operations, import a data, uh, also create some variables, rename some variables, do basic statistical operations, and leading up to regression. The objective of this video is not to teach statistics to R, but to see how does one perform some of the basic statistical operations using R. So in other words, whenever we use a statistical distribution, a statistical test, or any estimation, we are not going to discuss why we are doing that or when should we do this particular technique. We are only focused on what are we doing here. Okay, so for the part of why and for the part of when to do it, we will have detailed sessions in the classroom. But right now, let's kind of just get used to R so that you can download R when you are in the class and ready to perform the operations in the classroom. Okay, so let's get started. Mm, so to download R, so uh, visit the website rstudio.com and go to R download, and what you will end up and it will take you to a screen like this. And depending upon what is the system you have, you download it. There will be a you download and you install, and the icon in the desktop will appear like this. So this is the RStudio icon that appears on the desktop. So if you click it, that's how the R will open. It's a 4-pen screen. I prefer the RStudio because I can see all what is happening in front of me. So in the main screen, this is where we input the scripts. This is where we run the commands. In the R console is where we get to see the output. Here we look at the history of whatever we have done, the data and the variables. And here in this screen, we have packages which can use to download, or we can also see the plots. So these are the 4 screens which we have. Now, along with the video, you will also find this particular script which has been there in this website, which has this notepad where I have inputted all the scripts. So what we will do is we'll just copy all the scripts which contain some of the basic commands, and then I'm going to just run them in the R and explaining that if you run them, what happens. So let's kind of pick up. Let's copy the scripts and let's kind of paste it in R. Okay, and we have about 222 lines of scripts. Now, before we start, note that any line which starts with a numeric sign, anything which comes after the numeric sign is ignored by R as a command, and it is just read as a text. So if I do this and if I just do a run, nothing is going to happen. Okay, so where do we create it? So we create something called we create it in the I create a working directory, which is my directory, and then I need to import a file. So when I'm importing a file, I'm going to name the data file as D2, which is a CSV file. So R is very apt in importing CSV files or text files, and we run this command, which is read CSV file, and we're going to choose the file, and we say header equals to T. So let's see what is the D2 file looks like. So this is the D2 CSV file. So you can convert any Excel file to CSV by doing file, save as, and when you have to save it, just save it as a CSV file. Okay, so let's go back to the file. Okay, so let's go to the D2 CSV file. Now, This is the NSS round 66 data. Now, what NSS round 66 does is every 5 years, the National Statistical Survey, they conduct extensive household surveys and trying to find out the consumption patterns, the consumption items, and which is subsequently used by the government and the policymakers to determine the income status of the household, the poverty status, and the other things of importance. So these are the household IDs. The state sector is, so let's kind of look at very quickly, go through the filter, the headings of the data. So we have state sector. The state sector is D2. D is for Delhi and 2 is for urban. So this is only the Delhi urban. Household size are numbers, numerics. So there are households which has only one member households. There are households which are 8 member households. The religion, there are, we have classified them into basic 1, 2, 3, 4, 5 religions. There are social groups where we have the OBC, the SCs, STs, and others. We also have the primary cooking material, whether it's an electricity, whether it's kerosene, LPG. Uh, the households, whether they have electricity or not. So households with 1 means they have access to electricity. Households with 0, they don't have access to electricity. The salary, whether the household, the primary wage earner in the household is salaried or not, and 1 means they are salaried, 2 means they are not. MPCE is the per capita, monthly per capita household expenditure, and this number, the NSS collects consumption expenditure on various items, and then they aggregate them, and then they compute the monthly per capita expenditure. Poverty line, this is the Delhi poverty line per capita, and the notion is that if these numbers are greater than this, then the household is above the poverty line. If they're low, if they're below, then the household is below the poverty line. So for example, this particular household is above the poverty line, while this particular household is below the poverty line. These are some of the assets. We have bedstead, we have almirahs, we have chair, radio, TV, fan, AC, stove, fridge, cycle, bike, and car. NSS actually collects many more assets than what is given here, but I've just picked up a handful of the assets. The original data set is much bigger. It has many more columns. I've just truncated the data to the basic minimum which we are going to use in the exercise and also in the classroom. And so basically, the 1 and 0 means that whether the households possess that asset or not. So for example, if you look at this particular household, the relevant data is this household has a 5 member household. They're Hindu. Their social group is others, which means they are neither SC nor ST nor OBC. Their primary cooking material, medium is LPG. They have access to electricity. They have a salaried member. The MPC is 2351 above the poverty line. They have a bed, they have an almirah, they have a chair, but they don't have a radio, they have a TV, they have a fan, they have an AC, they have stoves, they have fridge, they don't have cycle, they don't have bikes, and they don't have car either. So one important part is that the requirement of these assets are just to use as a classification, that we are going to say that the households having a particular asset are more likely to be poor or not poor. So it's not that the having these assets are going to make them more poor or not poor. So having these assets does not explain a household becoming poor. It's the other way around. If a household is poor, it's more likely to have not have an asset than than having an asset. So that's the data which we have in the CSV, and so now let's kind of read the data. So let's kind of read the data. So if we read the data, we read it, and very soon it will prompt a screen, so we can see that it's doing something. So let's kind of just minimize the window, and it says let's read the CSV data. So we open the CSV data. So let's go back to R. Okay, so we have 842 observations and 22 variables, and let's kind of attach the data. So this is the data on which we are going to work. Okay, fine. So now we need to kind of attach certain packages. So how do we attach certain packages? In my case, some of these packages are already installed. So you will also have to install these packages, but let me just tell you how does one install some packages. So let's go to packages, and suppose I want to install the package which is, let's say, something apcalc, which we are not going to use. We are not going to use in this particular video, but just to demonstrate how does one install this package. So let's go to apcalc. So this has been installed, but just installing this is not going to be good enough. So what we have to do is we have to also put that in the library so that when we need, it can be done. So let's kind of do it, apcalc, okay, and then let's kind of run the packages, and this is what we get. Because we have run all the packages, so all the installed in the library, so they can be used. Okay, so we are set to kind of use art. Now there is one small word of caution. R is case sensitive, so if we write something which is which if you're not careful, then it is not going to kind of help us. It will not allow us to progress. So first, let's check the dimension of the data. So dimension of the data. So it has 842 rows and 22 columns. Okay. Next, let's kind of learn how to create some variables. We will try to create some variables, and let us see how does one create some of the what we call the dummy variables. So let's look at the D2, and let's look at this variable religion. So this variable is not numeric. So this variable is not numeric because it is Hindus, it's Islam, it's alpha, it's alphanumeric. So what we need to do is we have to convert them for our use, and we are going to create a dummy variable where dummy variable will be something like we'll create a variable called Hindu, so that every time a household is Hindu, it will get 1, and if it is not an Hindu, it will be given as 0. So let's kind of, how do we create that? Let's say Hindu. So if else the variable was religion. So if the religion is Hindu, then 1, otherwise 0. So let's kind of run it. So we have already created a variable Hindu, so which you can see. These are 1, and this is how it goes. It's 1s and 0s. Similarly, poverty. Poverty is an indicator variable that if the MPC is less than the poverty line, it's 1, otherwise 0. So let's also run poverty. And let's run the others also. Okay. Now, notice in the original data, this was a variable which is not numeric. This is a variable not numeric. This is not a variable numeric. This is a variable which is again an indicator. So this has already been coded in the original data as household having electricity is 1 and the household not having electricity is 0. So we don't have to rename or do anything about this variable, but we have to do something about this variable, because here the 1 and 2 it's not numeric. These are just indicators. So 2 doesn't mean greater than 1. So what we have to convert them, the salary income, is to a particular variable where if the household has any member who had the salary income, then that household will get a value 1 and rest all households will get a value 0. So I have to kind of create the salary. So it's again an if else, except that now instead of this being an alphabet, or I'm going to just put numerics. So it's 1 and 0. Finally, we create a variable log MPC, which is nothing but log of MPCE, and later on in the video it will be clear that why we are doing a log of MPCE. Right, so we are all set. So let's kind of start working on it. The first thing is let's kind of do a summary stat, and with any data, that's the first thing which we should do. So let's do a summary stat. So we get a summary stat of household size. So the minimum is 1. There is a household which has a minimum size of 1. The maximum is 12, and the mean household size is 3.657, and the median household is 4. Okay. Similarly, we can do it for the others. Okay, we can do it for poverty. Poverty, on the other hand, the mean is 0, maximum is 1. Summary of MPCE. Okay, the mean is 2961, that's the maximum. There is a per capita household expenditure of 23,000, and the summary of log of MPC. So let's do all this summary. The summary, so let's do log of MPCE. Okay, so this is the summary of log of MPC where the mean is 7.775, and this is what we have. Okay, so now about some basic descriptive statistics. So let's pick up the household size. Say the mean household size happens to be 3.65677. That's what we had observed earlier, remember? 3.6577. The median household size is again 4. The variance of the household size is 4.63, and the standard deviation is 2.15. Okay, so that's the summary stats which we have. Similarly, the mean log of MPC is 7.775, and the standard deviation is about 0.64. I'm not running the skewness and the kurtosis scripts now because we will do that later. The next thing to be done with the data is doing a simple graphical representation. So let's start with a pie chart. So let's kind of start the count, and I'm using religion. And so let's just run count, and it will show that, okay, so these many total items, so this should add up to 842. There are 701 Hindus, 103 Islams, 5 Jains, 27 Sikhs, and 6 Christians. And if I now do a pie chart, this is how it looks. Obviously, 3/4 of the data is, 3/4 of the data, the 3/4 of the households in our sample, their religion is Hinduism. Okay, so let's do a histogram, the household size with the frequency, and this is how it looks like. There are a lot of households with 2 members and 1 member household, and there are some household members with 12. Let's do the line. And what we get is something like a bipolar. So there are two modes of this. So there are 2 peaks of this. We will talk about the implications of this later, but let's just go on with this. Let's do the histogram of MPCE. It again looks very skewed. It goes up and then it goes down. And let's look at the histogram of log of MPC. Histogram of log of MPC surprisingly looks now very, very symmetric. So, and some of you who have already have some idea about the Gaussian distribution or the normal distribution would probably agree that this is how most probably a normal distribution looks like. Okay, but whether it's a normal distribution or not, we need to kind of formally check. But one thing which we can do in between is just kind of check what was the skewness and the kurtosis of these. So if it's a normal distribution, we know it should not have any skewness. It's indeed quite small, 0.28, which means it is reasonably symmetric, and nor should it have a very high peak or be too flat. Again, the excess kurtosis is about 0.06, and so it's not very high. Again, in the classroom, we will know that how high is high and how low is low, but let's kind of skip that for a moment and just kind of run how to do the basic tests. Let me now do a 2-plot, a scatter kind of plot, where I plot household size on the x-axis, log MPC on the y-axis. I want to label the x-axis as size. I want to label the y-axis as MPC. And if I plot it, this is what I get. So visually it looks like there is going to be a negative relationship between the two. So which means as household size increases, you can see that the MPC, that it's going down. In other words, there seems to be an a priori hint that or an a priori possibility that the bigger household sizes, the households with more members are more likely to be poor. But it doesn't mean that having a more member of having more family members increases the chance of poverty. It doesn't mean this from this data. It just says that if you look at if you divide the population into two groups, people who are poor and people who are not poor, you are more likely to observe that the population with below the poverty line have on an average a bigger household size than population above the poverty line. Now, to find a correlation between the two, we should expect a negative correlation, and indeed we get a negative correlation. Okay, so that takes care of the basic descriptive part of the data. Let's do some basic probability distributions. Let me first start with some of the discrete probability distributions. Let me start with the binomial. So this is the point probability. So in other words, what this is trying to say is we are trying to find out what is the in a Bernoulli trial, in 20 such tries, given that the probability of success is 0.13, what is the probability that there will be 4 successes? So that's D binom, and what we get is 0.149, so it's about 15%. There's a 15% chance that out of 20 trials there will be 4 successes when probability of each success is about 0.13. The cumulative is P binom, so this says what is the probability that in 20 trials there will be up to 4 successes. So that number happens to be 0.89. In other words, it is about 89% chance that in a Bernoulli trials of 20 where probability of success is 0.13, there are going to be up to 4 successes. We can also cross check if we actually add d binom 4 plus d binom 3 plus d binom 2 all up to d binom 0, you should get the same value, and that's a small exercise which you can try. Let's look at the Poisson probability, the point probability. So this is the point probability. So what is the probability that given you expect 4, there will be 8 such successes. So you expect 4 to happen and 8 such successes, and if I do it, it happens to be 0.02. So there's a 3% chance that you are expecting 4 and actually 8 will happen. The next one is what is the probability, this is a cumulative, that you are expecting 4 and up to 8 successes happen, or up to 8 such occurrences happen. So that's about 0.978. So in other words, to interpret the data, if you look at the household size, if the median household size was equals to 4, if you remember, then the probability that you will come across households which is greater than 9, will be less than 2%. So if there are some households whom you want to identify as outliers because their the household size is an extremely rare event, so you can probably think about screening those households which have more than 9 members, maybe 10 or 11, 12. Okay. So going by that, that's the Poisson probability and the binomial. So let's look at some of the continuous distribution. So let's start with the normal distribution. And so what is the probability of if something follows normal distribution with mean 7.775 and standard deviation 0.64, what is the probability that it's going to be? Okay. So what is the probability that it's going to be so greater than 9? So remember, it's the lower tilt equals to false, so we are looking at the upper tail. So in other words, we are looking at basically what is the probability that x is greater than equals to 9 when the mean value of x is 7.775 and standard deviation is only 0.64. If you want to find the other way, then what is the probability that x is going to be less than equal to 9 when mean is 7.775 and SD is 0.64, then you do lower tail equals to t, and it will be nothing but 1 minus what we had previously. So this is nothing but 1 minus this. So the probability of up to 9 is 0.97, probability of beyond that is therefore is 0.027. Okay. Now, having done the normal distribution, let's do a quick thing. Let's kind of check whether a data is indeed normal distribution or not. So the best way to check whether the data is a normal distribution or not is to run some tests. But to understand the tests, let's kind of first create 1000 random numbers. and I'm using R norm, which is a random number for normal distribution, 1000 random numbers, mean 0 and standard deviation 1. So let's kind of create that. So we have created that. Let's look at the histogram of that. And indeed, the histogram looks like, it looks slightly skewed, but okay, maybe that's what it says. This is what the histogram looks like. So let's kind of go with that. Let's do the QQ norm. So this is basically we are plotting this, and had it been a normal distribution perfectly, it should have been exactly on this 45-degree line. And if it deviates from the 45-degree line, then it's not a normal distribution. So let's kind of color that line in red. So I've used the color red so that I know exactly, yeah, this is the line, and therefore mostly it's on the line, but there are some which is not on the line. Okay, so let's kind of do some tests and to check whether they are indeed normal distribution or not. The first one is the Shapiro test. So let's run the Shapiro test. Okay, and once I run the Shapiro test, I get a p-value of 0.04, and which means that the original data is a normal distribution. That the original data is a normal distribution. That there is a chance that it is not a normal distribution. So there is with a 95% confidence level, I can possibly say that it's not a normal distribution. Okay, let's move on to the next step, the Anderson-Darling test. The Anderson-Darling test says, again, that the original data is not a normal distribution. It's possible with a probability of there's a 97% chance it's not. Let's do the Kolmogorov-Smirnov test. In the case test, we have to specify the mean and standard deviation which we are checking. And then the Kolmogorov-Smirnov says that there is a 99% chance it's not a normal distribution. So probably the random numbers which we had drawn did not work out. So let's kind of see if we can do better with another set of random numbers. So let's do another set of random numbers. And let's do the histogram again. Okay. So now this set of random numbers suddenly, by the Shapiro will test it is 0.39. So it's the null hypothesis that it's a normal distribution now cannot be rejected. By the AD test, it's again 0.30. Neither can you reject the original by the original the new set of random variables as normal distribution. And when I do a case test, again it's 0.36. So in all the so this set of random numbers which I've drawn is actually very close to being a normal distribution. So one word of caution is that when we draw a random number, often as you can see that it is not automatically guaranteed that the random numbers drawn by the software will always follow the prescription which you want them to. Okay, so having done that, let's kind of see whether the MPC follows normal distribution or not. Okay, so let's try run the MPC. Well, the MPC doesn't because the p-value is extremely small, so it's not a normal distribution. By the AD test, it's again, its A is very large, so therefore by AD test also rejects the fact that MPC follows normal distribution. And when I do the KS test, specifying the mean and the standard deviation, and when I run this, okay, it's again this very small p-value, and therefore now the MPC is not a normal distribution by all the three possible tests, and with a very high level of significance. But what about the log MPC? If I do log MPC, then by the Shapiro test, well, it doesn't follow a normal distribution. By the AD test, at a 95%, with about at a 95% level, you are going to accept the fact that yeah, indeed it follows a normal distribution. And if I do the case, we're again going to accept the fact that it's a normal distribution. So in a real data, you can often have that there are 3 or 4 tests which you do. Some of them give a particular outcome, the other two gives another outcome, and one has to use. We have to know exactly what has to be interpreted from this data. Okay, so that was the normal distribution. So let's look at t distribution, and I'm going to just talk about how to find out the t values from the degrees of freedom. So if I do qt with the 2.5% and 97.5% with 10 degrees of freedom, what I get is These are the ranges. If I do chi-square with 0.95 and degrees of freedom is 10, I get 18.30. And if I do f-test with the numerator degrees of freedom being 5 and denominator degrees of freedom being 2, what we get value is 19.29641. Okay, so these are the one general rule. We should use the d poise and d binom etc. for point or density, and p poise and p binom for cumulative density.